Welcome to our introduction to cryptography, the essential science of securing communication in our digital world. This field is absolutely vital for protecting information and ensuring privacy in today's interconnected digital age. Today, we will compare symmetric and asymmetric encryption, two fundamental approaches to secure your data effectively. These represent two distinct yet powerful methods for achieving robust data security in different scenarios. Let's begin by examining how keys are used in each of these encryption types for securing messages. Symmetric encryption utilizes a single, shared secret key for both encrypting and decrypting the information. Asymmetric encryption, however, uses a unique pair, a public key for encryption and a private key for decryption. Next, consider the performance aspects. How fast and efficient are these encryption methods? Symmetric encryption is generally much faster and more efficient, ideal for encrypting large volumes of data. Asymmetric encryption is typically slower and requires more computational power due to its complex key operations. Now, let's discuss key management, a critical aspect of securely distributing and handling these keys. For symmetric encryption, securely exchanging that single secret key between parties is a significant challenge. In asymmetric encryption, the public key can be shared openly, while the private key remains secret and secure. Finally, let's look at the best use cases for each method to understand their practical applications. Symmetric encryption is best suited for efficiently encrypting large quantities of data due to its speed. Asymmetric encryption excels in secure key exchange and for creating digital signatures, ensuring authenticity. Let's delve deeper into symmetric encryption and see how it actually works to protect your data. Symmetric encryption uses one secret key for both encoding and decoding. Plaintext becomes ciphertext, then back to plaintext, requiring secure key exchange. Now, we will explore asymmetric encryption, also known as public key encryption, and its unique mechanism. Asymmetric encryption uses a public key to encrypt and a private key to decrypt. This simplifies key distribution while maintaining strong security. Let's explore the essential properties that make a hash function strong and reliable in cryptography. These are the key characteristics defining a strong digital fingerprint, crucial for data integrity and security. First, a hash function must be deterministic, meaning it consistently produces the same result. This means that if you give it the exact same input, you will always get the exact same output hash. Another vital property is that the hash output must always be of a fixed size. Regardless of how large or small your input data is, the resulting hash will always have a constant length. Next, we have preimage resistance, a property that makes it incredibly difficult to reverse the process. It means it's computationally infeasible to figure out the original input data just by having the hash output. Then there's collision resistance, which is absolutely critical for security applications. It should be practically impossible to find two different inputs that produce the exact same hash output. Finally, the avalanche effect ensures that even tiny changes drastically alter the hash. Even a single bit change in the input should result in a drastically different and unpredictable hash output. Now, let's walk through the step-by-step process of how a digital signature is actually created. These steps are essential for ensuring both the authenticity and the integrity of your digital messages. The first step involves hashing the message, creating its unique digital fingerprint. The sender uses a hash function to create a unique digital fingerprint, or hash, of the original message. Next, the sender signs this hash, making it their unique, verifiable mark. This hash is encrypted using the sender's private key, which then forms the actual digital signature. The final step is for the recipient to verify this digital signature's authenticity. The recipient decrypts the signature with the sender's public key, comparing it to a newly computed message hash. Let's now examine the fundamental building blocks that constitute a robust public key infrastructure. These components form the essential framework for establishing and managing secure digital identities. First, we have the Certificate Authority, or CA, a trusted entity that issues digital certificates. Then there's the Registration Authority, or RA, which verifies identities on behalf of the CA. Digital certificates are crucial. They bind a public key to an identity, proving ownership. Of course, public and private keys are central to PKI, enabling encryption and digital signatures. Finally, the Certificate Revocation List, or CRL, tracks certificates that are no longer valid. Now, let's explore the life cycle of digital certificates and how PKI effectively manages them. We'll cover the entire process, from a certificate's initial issuance all the way to its potential revocation. The first step is certificate issuance, where a CA verifies identity and then creates the certificate. A certificate authority issues a digital certificate only after thoroughly verifying the requester's identity. Once issued, certificates are used for various secure communication purposes. Certificates are used to encrypt data or verify digital signatures, securing communications effectively. Next comes certificate validation, where users confirm its authenticity and validity. Users verify a certificate's authenticity and validity, often by checking against a certificate revocation list. Lastly, certificate revocation happens when a certificate needs to be invalidated prematurely. The CA updates the CRL to invalidate a certificate if it needs to be retired before its official expiry date. Today, we'll dive into how a secure SSL/TLS connection is established, a critical step for online safety. The SSL/TLS handshake is crucial, as the client and server agree on encryption protocols and authenticate using digital certificates. Now, let's explore the many places where SSL/TLS actively secures our digital world and protects our online activities. Specifically, we will look at how SSL/TLS is essential for protecting various forms of online communication we use daily. First up is web browsing, a fundamental area where SSL/TLS plays an indispensable role in our daily internet use. It secures HTTPS connections, ensuring that your data exchanged between your browser and websites remains private. This encryption protects data moving between your browser and websites, safeguarding your sensitive online interactions. Next, let's consider email, another critical area where SSL/TLS provides essential security for your communications. It protects protocols like IMAP, POP3, and SMTP, which are vital for sending, receiving, and managing your emails. This protection prevents unauthorized interception and tampering, ensuring your email messages remain confidential and unaltered. VPN, or virtual private networks, also heavily rely on SSL/TLS to create secure and private connections. SSL/TLS secures these virtual private network connections, creating a safe tunnel for your internet traffic. It provides encrypted access to remote networks, allowing you to connect securely from anywhere in the world. Finally, let's look at e-commerce, where SSL/TLS is absolutely critical for secure online transactions. It protects your sensitive financial information, such as credit card details, during online purchases and transactions. Crucially, it also verifies the authenticity of online transactions, building trust and confidence in your purchases. To conclude, let's summarize the key takeaways from our discussion on cryptography and its essential role. These are the essential concepts that underpin digital security, protecting our information in the modern world. Remember, cryptography fundamentally secures information by transforming it through both encryption and decryption processes. Symmetric encryption uses one key for speed, while asymmetric encryption uses two keys for secure communication exchange. Hash functions are vital. They ensure data integrity by generating unique digital fingerprints, detecting any alteration. Digital signatures offer authenticity, integrity, and non-repudiation, confirming the sender's identity and message validity. Public Key Infrastructure, or PKI, manages digital certificates to build trust and securely verify online identities. Finally, SSL/TLS protocols establish those secure, encrypted communication channels, safeguarding our online interactions effectively.